Welcome to section 4.3 differentiation mean value theorem. This is Dr. Gilbert Eyabi. We are using the text Advanced Calculus by Patrick M. Fitzpatrick, second edition. Any text would be okay as long as we're dealing with MVT, the mean value theorem. Let's start with a remark. Subsection 4.3.1. The mean value theorem is one of the most useful and geometrically attractive results in calculus. It simply asserts that if f is a real valued function from the domain which is a closed bounded interval AB, if f is continuous and its restriction to the open interval AB is differentiable, then there exists a point x0 in the open interval AB such that the tangent line to the graph at the point x0 f of x0 is parallel to the line passing through the points A f of A, B f of B. Let's look at that geometrically so we can see what we are talking about. So right here, this is our function f of x. That's the point A, that's the point B. So this point is A f of A and this point is B f of B. So this is the line that passes through the points A f of A, B f of B, and the slope of this line would be the rise divided by the run, which is f of B minus f of A divided by B minus A. So that is the slope of this line. So we say there exists a point x0, and this is our x0. And this is the point x0 f of x0. So there exists an x0 in the open interval AB such that this point x0 f of x0, the tangent line through this point, so that's the tangent line through that point right there, the slope of the tangent line through this point is just f prime at x0. So if this line is parallel to this line, what we are simply saying is that the slope of this line would be equal to the slope of this line. So MVT simply says that the slope of this tangent line through the point x0 f of x0, which is f prime at x0, equals the slope of the line through A f of A, B f of B, and that is f of B minus f of A divided by B minus A. So that's what MVT is. But the real statement of MVT would be, suppose that the function f from the closed bounded interval AB to R, which is the set of real numbers, is continuous, and its restriction on the open interval AB is differentiable, then there exists a point x0 in the open interval AB at which f prime at x0, which is the slope of this tangent line at the point x0 f of x0, equals the slope of the line through A f of A, B f of B. We're going to prove it, but we just wanted to introduce the theorem first under remarks. Let's go ahead and start looking at the section a little bit at a time. 4.3.2 lemma. Let I be a neighborhood of x0. I is an interval, so that means x0 is an I. And suppose that f is a function from I to R, where R is the set of real numbers. Suppose that f is differentiable at the point x0. If x0 is either a maximizer or a minimizer of f, then f prime at x0 is 0. I hope you can remember what a maximizer is. x0 is a maximizer on an interval I if f of x0 is bigger than or equal to f of x for every x in the interval I. Similarly, you can define what a minimizer is. So right here, what we are saying is if this point is x0 and it's a maximizer, then the first derivative of f at that point is 0. And if this is x1, it's a minimizer, the first derivative at this point is 0. Now we're going to look at the proof more formally, but if you look at it interestingly, this is the tangent line to this point right here. And guess what? The tangent line is horizontal. The slope of this tangent line through this point is 0. Same thing. It's a horizontal line. So the slope of the tangent line through this point is 0. As easy as that. You could actually use that as a kind of proof if you can explain it a little bit clearly. But we're going to give you something a little bit more formal. Proof. By the definition of a derivative, the limit as x approaches x naught from the left of f of x minus f of x naught divided by x minus x naught must be the same as the limit as x approaches x naught from the right of f of x minus f of x naught divided by x minus x naught, and that equals f prime at x naught. That is the definition of the derivative, and we're adding the fact that a limit exists if the left-hand limit equals the right-hand limit. So we are putting all of those together. Now let's see how we're going to use that concept in our proof. Let's start off with the case where x naught is a maximizer. If x naught is a maximizer, then f of x is less than or equal to f of x naught for every x in I, in which case f of x minus f of x naught is less than or equal to 0. So that is negative or 0. Now look at x minus x naught. If x is less than x naught, then x minus x naught is negative. Negative divided by negative, so we have greater than or equal to 0. What this means is, if I take limit as x approaches x naught from the left, which means x is less than x naught, of f of x minus f of x naught divided by x minus x naught, then the denominator is negative. The numerator is less than or equal to 0. So the entire limit is greater than or equal to 0. Call that inequality 1. Let's go slowly. What happens if x approaches x naught from the right? In which case x is bigger than x naught. Then the denominator is positive. The numerator is still negative because x naught is a maximizer. Right here, f of x minus f of x naught is less than or equal to 0. So negative divided by positive, we have less than or equal to 0. That means f prime at x naught, which is the limit as x approaches x naught from the right of f of x minus f of x naught divided by x minus x naught, is less than or equal to 0. Call that inequality 2. So what we have here is that f prime at x naught is bigger than or equal to 0. F prime at x naught is less than or equal to 0. 1 and 2 implies that f prime at x naught equals 0 when x naught is a maximizer. Similarly, just reversing the inequalities, we can prove that f prime at x naught is 0 if x naught is a minimizer, and therefore we can conclude that if x naught is either a maximizer or a minimizer of a function f from an interval I to R, the set of real numbers, then f prime at the point x naught is 0. The reverse is something else. If f prime at x naught is 0, does that mean that x naught is either a maximizer or a minimizer? Not necessarily. We're going to leave that as the last thing we shall see in section 4.3. We need an additional step to be able to conclude if our x naught would either be a maximizer or a minimizer. Beautiful. Our next stop would be Rolle's theorem, subsection 4.3.3. If f is a function from a closed bounded interval AB to the set of real numbers R, and f is continuous, and the restriction of f to the open interval AB is differentiable, assume also that f of A equals f of B, then there exists a point x naught in the open interval AB such that f prime at x naught is 0. Proof. Since f is continuous by the extreme value theorem EVT, it attains both minimum and maximum values on the closed bounded interval AB. Done. Now, since f of A equals f of B, we have two options. Number one, If both the maximizer and minimizer occur at the endpoints, then f is a constant function, in which case f prime at x0 is 0. We would leave that as a simple exercise for serious students. Prove that f prime at x0 is 0 if f is a constant function. Use the limit definition of the first derivative. And that actually holds for every x in AB. So in particular, it holds for x0 since x0 is in the open interval AB. Number 2, the function has either a maximizer or a minimizer at some point x0 in the open interval AB. Then by the lemma that we've just seen, f prime at that point x0 will be 0. And that brings us to the end of the proof of Rolle's theorem. Now we go ahead on with the theorem of the day, subsection 4.3.4, the mean value theorem. Let f be a function from the closed bounded interval AB to the set of real numbers R, and f is continuous on that interval, differentiable on the restriction AB, open interval AB. Then there exists a point x0 in the open interval AB such that f prime at x0 equals f of b minus f of a divided by b minus a. In other words, the slope of the tangent line through the point x0 f of x0 equals the slope of the line through the point a f of a b f of b. For a number m, we wish to apply Rolle's theorem to the function h from the closed bounded interval AB to the set of real numbers defined by h of x equals f of x minus mx, where x is in the closed bounded interval AB. To do so, we must have h of a equals h of b, so we can apply Rolle's theorem. This occurs precisely when we chose m to be f of b minus f of a divided by b minus a. We leave that as a simple exercise for serious students to investigate. Now for this choice of m, we apply Rolle's theorem at which h prime at x0 equals 0. Since h prime at x equals f prime at x minus m, because the first derivative of this would just be f prime at the point x minus m, since the derivative of mx is m. So since h prime at x equals f prime at x minus m, at this point x0 we would have f prime at x0 equals f of b minus f of a divided by b minus a. Simple investigation. We leave that as a simple exercise for serious students. Now it appears the proof of MVT is really short. The reason is because we've had a couple of lemmas, Rolle's theorem, and a few other things that we are putting together to make the proof very concise. And that is the proof of the mean value theorem. Section 4.3 does not conclude without a few extras. And one of them is subsection 4.3.5, which is a lemma. And the lemma says that if f is a function from the interval I to R, where I is an open interval and f is differentiable, then f is a constant function if and only if the first derivative of x equals 0 for every x in I. In other words, f is a constant function if and only if f prime equals 0. Forward direction. Suppose f is a constant function. Let's prove that the first derivative is 0. I already mentioned that before, so I'm going to leave it as a simple exercise for serious students. Just use the definition of the derivative, the limit definition of the derivative, and you realize that f prime at the point x0 is limit as x approaches x0, f of x minus f of x0 divided by x minus x0. But f of x will be the constant c. F of x0, the constant c. C minus c, 0. First derivative, 0. And we're done. I'll let you fill in the gaps. The reverse. Suppose the first derivative is 0 at every x in I. We want to prove that f is a constant function. Choose x0 in I and define f of x0 to be c, where c is a constant. We will show that f of x equals c for every x in I. Let x be an element in I and suppose that x is less than x naught. So follow the argument very carefully. Since differentiability implies continuity, the restriction of f to the interval x naught, see the restriction right there, is going to be continuous, and the restriction to the open interval x naught is also differentiable. So now we have f continuous on the closed bounded interval and differentiable on the open interval. So we can apply the mean value theorem. There exists some point z. We don't want to use x naught because x naught is already in the question. So there exists some point z in the open interval x naught such that f prime at the point z is f of x naught minus f of x divided by x naught minus x. But if f prime at z equals 0, that means f of x equals f of x naught, and that equals c. And that happens for every x less than x naught. So we're going to try a similar argument for every x greater than x naught. And we would simply say, use a similar argument to conclude that f of x equals f of x naught equals c for every x greater than x naught, and call that equation 2. Now, if you missed it, observe that if f prime at z equals 0, then if I cross multiply, I would end up with f of x naught minus f of x equals 0, in which case f of x naught equals f of x. But f of x naught equals c. So we have f of x equals f of x naught, which equals c, and that holds for every x less than x naught. Again, using a similar argument, we conclude that f of x equals f of x naught equals c for every x greater than x naught. We already have it that f of x naught equals c, f of x equals c for every x less than x naught, f of x equals c for every x greater than x naught. We put all of those together, 1 and 2 plus what we already defined up here, we can conclude that f from I to R is a constant function, i.e. has a constant value c, end of proof. Very easy and very beautiful. Our next stop in section 4.3 would be subsection 4.3.6, the identity criterion. Let I be an open interval and let G and H be functions from I to R, where R is the set of real numbers. Suppose G and H are differentiable. Then these functions differ by constant if and only if their first derivatives are the same. In other words, G minus H equals some constant C if and only if G prime equals H prime. Proof. Forward direction. Let's define f to be the function G minus H from I to R. You don't have to define it. You can just work with G minus H directly. Actually, it's a lot easier to do that. Now, by the sum rule or the sum property for derivatives, we know that the derivative of the sum equals the sum of the derivatives. So f prime would just be G prime minus H prime, i.e. f prime of x equals G prime of x minus H prime of x for every x in I. Now, if f equals G minus H, which equals some constant C, then by lemma 4.3.5, the first derivative of f is just going to be 0, i.e. G prime of x minus H prime of x equals 0, and that means G prime of x equals H prime of x, and the forward direction is done. The reverse direction, suppose G prime of x equals H prime of x for every x in I, then what we're saying is that G prime of x minus H prime of x equals 0 for every x in I. Again, by the sum property of derivatives, that means f prime of x equals 0, and by lemma 4.3.5, again, that means f of x equals c, where c is a constant. In other words, G of x minus H of x equals c, and that concludes the proof. So we really do not need the f. It's just an additional thing that probably brought more confusion than clarity. Okay, now we have another stop. Then I think one more. and we would be done with section 4.3. Subsection 4.3.7, strict monotonicity criterion. Let I be an interval and let f be a function from I to R, the set of real numbers, and f is differentiable. Suppose the first derivative of f is greater than 0 for every x in I. Then we conclude that f is strictly increasing. F is a strictly increasing function on the interval I. In other words, if x1 and x2 are 2 points in I such that x1 is less than x2, we want to show that f of x1 is less than f of x2. As easy as that. Okay? Now, x1 less than x2, we can apply MVT. F is differentiable on I. x1 and x2 are elements in I. So I can look at a closed bounded interval x1, x2. F is going to be continuous on the closed bounded interval x1, x2 and differentiable on the open interval x1, x2. So by MVT, we can actually find a point x0 in the open interval x1, x2 such that f prime at x0 is f of x2 minus f of x1 divided by x2 minus x1. The first derivative is bigger than 0. That is given, part of the hypothesis. Since x1 is less than x2, x2 minus x1 is positive. So we have positive. We have positive. If we cross multiply, positive times positive is positive. That simply means the numerator f of x2 minus f of x1 is greater than 0. In other words, f of x1 is less than f of x2, and that implies f is strictly increasing. And that concludes the proof of corollary 4.3.7, strict monotonicity criterion. A definition, one theorem, and we're done. Subsection 4.3.8, we're going to introduce the idea of local maximizer and local minimizer. A point x0 in the domain of the function f from D to R, the set of real numbers, is said to be a local maximizer for f, provided that there exists some delta greater than 0 such that f of x is less than or equal to f of x0 for every x in D, where the distance, the positive distance between x and x0 is less than delta. So we can simply say that x0 is a delta neighborhood maximizer. So x0 is a maximizer in a delta neighborhood, not the global maximizer, but just a maximizer within plus or minus delta from x0. Okay? So we call that delta neighborhood maximizer. It's just like somebody is, the maximizer in his delta neighborhood. Like you're the king of your neighborhood. But when somebody comes there, they realize that actually you are the king plus or minus one house from yours, So you are the guy or the girl plus or minus one house from you. So you are the delta maximizer in that neighborhood. Similarly, we can define delta minimizer. That's the local minimizer. And now you should have an idea on how to define a global maximizer and a global minimizer. But in section 4.3, we are interested in local maximizers and local minimizers. I'll leave the definitions of global maximizer and global minimizer as simple exercises for serious students. Our last stop in section 4.3 would be subsection 4.3.8, theorem. Suppose I is an open interval that contains the point x0, and suppose f from I to R, the set of real numbers, has a second derivative, and suppose that f prime at x0 is 0. Let me give you a little background. Recall that we did say that if x0 is either a maximizer or a minimizer, then the first derivative at the point x0 is 0. And we ask the question, if f prime at x naught equals 0, does that automatically mean that x naught is either a local maximizer or a local minimizer? Well, we didn't exactly introduce the word local then, so the question was, if f prime at x naught equals 0, does that mean that x naught is either a maximizer or a minimizer? And I did say that we would have to introduce something else before we can make that conclusion. And this is it. If f prime at the point x naught is 0 and the second derivative at the point x naught is positive, is greater than 0, then x naught is a local minimizer of f. And if the second derivative at the point x naught is less than 0, then x naught is a local maximizer of f. So the second derivative, positive, local minimizer. The second derivative, negative, local maximizer. So just remember, bigger than minimum, less than maximum. Okay, that's one way to remember that. Proof. Suppose f prime at the point x naught is 0, i.e. the first derivative at the point x naught is 0, and the second derivative at the point x naught is positive. The limit definition of the derivative of f prime prime at x naught would just be the limit as x approaches x naught, f prime of x minus f prime of x naught divided by x minus x naught. And we do know that f prime prime at x naught is greater than 0, so this entire limit is greater than 0. It follows that there exists a delta greater than 0 such that a delta neighborhood of x naught is contained in I. Simple exercise for serious students. So x minus delta, x plus delta, the open interval, is contained in I, and f prime of x minus f prime of x naught divided by x minus x naught is greater than 0 for every x on that delta neighborhood of x naught. That's just simple reasoning. Makes sense. So what we're saying is this. F prime at x naught is 0. This amounts to the assertion that f prime of x is greater than 0 if x naught is less than x naught plus delta, and f prime at x is less than 0 if x naught minus delta is less than x naught. Now, using these two inequalities and the mean value theorem, it follows that f of x is strictly greater than f of x naught on this interval. 0 less than absolute value of x minus x naught less than delta. That is the delta neighborhood of x naught. But this simply means that x naught is a local minimizer because f of x is greater than f of x naught for every x in that little delta neighborhood. Similarly, we can argue the case for f double prime of x naught being less than 0, in which case x naught is going to be a local maximizer. And that brings us to the end of section 4.3, the mean value theorem, and we will see you in further sections. Thank you and God bless you. Bye-bye.